Moving on in 13.4, we're going to talk again about projectile motion, again meaning from Calc 1. We talked about this a little bit. So this is more typical of what you actually see in a physics book. They introduce vectors very early in calc-based physics, and then you do projectile motion in this way. So we talk about projectile motion in particular because when we have a constant acceleration due to gravity, which we have close to Earth, then this is how particles behave when there is not air resistance. We're not including that part. So I'm going to do a general derivation here, and you will be given the general formula on a quiz or test, but you should go through the motions here trying to see where this formula comes from. Alright, so here we go. Newton's, I think, second law, force due to gravity, is F equals ma. Specifically, when, again, we're talking about something being a force acted on due to gravity close to Earth, we have the gravitational constant g. In SI units, it's 9.8 meters per second. And I would give that to you. You don't have to memorize that. It's different in English units. It's 12 point something, whatever. So you don't have to memorize that. It's negative because it's directed down. And you can see with this parabola here, with the projectile motion, then we have this constant acceleration shown in pink here, and that's going to be directed in the j direction. And when we're in 2D here, we're taking j as the vertical, and it's just g units in the j. Again, negative because it's down relative to the motion, particle, ball, whatever. So if we're trying to find the position function, kind of showing that it's this parabolic motion, we're going to use integration. So same type of thing that we did in that specific example, but we're doing it in general. So specifically, we have the acceleration due to gravity is negative gj. Integrate that. G is constant. So we just have a value. When you take its integral, it's times t then. And that's in the j, plus our constant c. So kind of like we observed in the last example, that the initial velocity is when t equals 0. So whatever that may be, that initial velocity, we'll call it v naught, and that's specifically what that constant c will be. So we could just kind of give it a more specific name, and it's useful in our formulation because that's something that's typically given or we're supposed to find. Alright, anyway, so here we are with our velocity little vector function. So if we want to find the position function, we move on. We take the integral of our velocity vector. So doing that, we get negative 1/2 gt squared in the j, and then we have our v naught integrated, and so it's going to be times t plus another constant k. So noting again that typically we know the initial position, or when t equals 0 what the position is. We'll call that r naught. There should be a line there. So that's what our big constant k is. I'm not drawing in because the rest of my text boxes below will get messed up. Anyway, I think you can deal. So once we plug that in, we get this formulation here. So it's a little, maybe you noticed this already, that it's kind of weird in the sense that like we have this j component here, but then we don't have the component wise worked out for our v naught and our r naught. But it should look familiar in some form, again from physics or Calc 1. So if we want to do this in terms of components, which would be useful, just do a little bit of trig here with the initial velocity vector. So that's shown in orange, and if you break it up into components, then we can write it out in its components as a vector. So we have the magnitude of the initial velocity, and then we're going to have a y and an x component. So doing the trigonometry here, the cosine of theta is equal to that x component over the velocity's magnitude. Do a bit of algebra there, let's multiply, and then we get our component of the initial velocity for x. Simply the sine of theta to do for the y. And so now we got that. So kind of one of these notation things, and I indicated that up above, that now for the vector, its initial velocity magnitude, we're just going to use v naught in the cursive there, and it's understood it is a magnitude in that context because we're not writing it as a vector. So going with that, we have the notation as you have in your book, and probably physics books as well. So that's pretty standard. And one thing here in purple, just a little detail here, that pretty much we have initial position. We line up the x-axis with moving forward at t equals 0, so really the only factor here is if we're starting at a height that is above where the particle or ball or whatever it is would land. So it's directed some height in the positive y or j direction. So now we have those things defined in terms of their components. So then we can put this back into this formula we got. There it is. And then we can rearrange this and put it in terms of components. So finally we have the position function with this projectile motion due to gravity. It's this parabolic form as v naught t cosine theta in the I. And in the j we got a little bit more going on here. We have negative 1/2 gt squared plus v naught t times sine theta plus h. So this is given. Really slightly different than the formulation in your book, in that your book doesn't have the plus h, but we'll just put that in there because they do that in physics, so just kind of be more consistent. So we're ignoring error resistance. That would kind of change things up a bit, but we'll deal with the ideal. Let's do an example. This one's kind of fun. Example 3, we have a baseball. It's hit 3 feet above the ground level at 100 feet per second at an angle of 45 degrees with respect to the ground. Find the maximum height reached by the baseball. Will it clear a 10-foot high fence located 300 feet from home plate? So presumably we're talking about a home run here. So we have two questions. Let's focus on the first question. Find the maximum height reached by the baseball. Okay, so we're talking about height. Not talking about how far in the x, we're talking about height. And so this is the beauty of having this component representation of the projectile motion, because this is the only part we care about for now. And we have that parsed out. So if you remember from Calc 1, something typical when we're finding the maximum of a function is we use something called the first derivative test. So just as its name implies, the first derivative test has to do with taking the first derivative. You set it equal to 0, and then you solve for t. Oh, so trying to be a good problem solver here, I did note some things that were given in terms of the equation up here, which we're going to use some stuff in here. So height is 3 feet, initial velocity is 100 feet per second, theta is 45 degrees or pi over 4. G that's appropriate here is 32 feet per second. I misspoke earlier when I said it's 12 something. I don't know what I was thinking about, some other constant. Anyway, I would give that, so I didn't give it here, but I would give it to you. I promise. Alright, so I got that stuff out of the way. Now let's get to the first derivative test. So you take the derivative, set it equals 0, solve for t. Now there's some details, but pretty much if you only get one t there, and in this problem we know from the setup that at that t where you have y of t, y prime of t equals 0, that's going to be the maximum. So I kind of not being super good about showing the rest, but just deserves a call out. Alright, let's move on here. Here is our equation. I put it down here again because it's kind of off the page that's given. And so notice that we got the j or the y component right there for the purposes of this problem. That's what we care about, and that's our y of t. So we're going to take the derivative of that with respect to t and set it equal to 0. Also plug in g equals 32 so that the like units apply here. We also know that theta is pi over 4. So initial velocity is 100. So we plug all that stuff in, setting it equal to 0, do a bit of algebra to solve for t. So this ends up being pretty straightforward. We just get one t. That is the t. We can see from our cool picture here the baseball player that, you know, this parabolic motion of the projectiles, that's what's going on here. So that's about 2.21 seconds. And so, sorry I keep scrolling here, but what exactly was the question? Find the maximum height reached by the baseball. So it's not asking for the time, it's asking for the actual height. So you need to take that time and plug it in to just this y of t here, not y prime of t, but into the y of t to find that height. So I used my exact answer just to try to make this as perfect as possible along the way. And you can boil it down actually to an exact answer of 81 feet. Oh, about 81 feet. Here's the exact answer, sorry. 649 divided by 8. So we're done with that one. Now we're moving on to the second question. Will it clear the 10-foot fence? For again, presumably a home run here. That's why we care about that. And just can't wait to know. Alright, well, we know the ball is 300 feet in the horizontal from where it was hit. This 81 feet, we're not sure where in the x this is occurring, so I mean, it would clearly be greater than 10 if it was attaining its maximum at the fence, but that would be quite the hit, folks. So, you know, we definitely can't assume that. We do need to have this x component come into play here. So we know it's 300 feet in the x, and we know the horizontal component of the position function. So we can just let 300 equal that component and find the time for which that would occur. So at 300 in the x, we can solve for t, plug in the initial velocity, the pi over 4, to boil that down. And so if we simplify a bit here, we can get it all the way down to 3 times the square root of 2, or approximately 4.24 seconds. So now we know the time at which the ball would be 300 feet from home base, and that's where the fence is. So plugging that time into the y component now will tell us the height at that time. So, ooh, look at this. We go down to the final calculation. We get 15 feet. So we can celebrate it was a home run since the wall's 10 feet. So that's where I'll stop this recording. We got one more to go.